Okay. Yeah. Hello, everyone, and welcome to our afternoon session. Today in the afternoon, we have with us Tarun Saini, who talked to us about statistics, basic statistics, in a set of 3 lectures, which will be on all 3 days at 2 o'clock, 2 to 3 will be Tarun's lectures. Tarun is a faculty member at Indian Institute of Science, and he has worked a lot on galaxy dynamics, as well as on cosmology. A lot of the statistical techniques he'll be talking about today have been used by him on his work in cosmology. And so we're really happy to have Tarun with us and looking forward to his session. I have also shared on the resources on the website this lecture set which he's given us of 23 pages, which has an extensive amount of stuff on statistics, which I'm sure will be helpful to everyone. So over to you, Tarun. Yeah. Tarun, you can share your screen. Yeah. Okay, that is your screen. Yeah?
Priya, hello.
Well,
can you see my screen?
Yes. Yeah, we can see it.
This?
Yeah.
Okay, fine.
Yeah, now I can see your board.
Okay. So, good afternoon, everybody. So hopefully, you have already downloaded these notes, or you can do it later. But these set of notes actually are very extensive, and I use them to in a course which was about 15 lectures or a little more, and the notes are very condensed. So it's obviously not possible for me to go through each and every topic that is in these notes. And there are some topics that are actually not covered in these notes also, which I would wish to inform you about. So instead of making these 3 lectures as some sort of a mini course or even a primer, I'm going to basically use these 3 lectures to actually introduce you to certain concepts which you are very likely unfamiliar with. But these concepts will actually help you learn more about statistical techniques as they are used in various disciplines of science. So let me switch to the board. So the main disciplines in which statistics is used in science, one of them would be wait. So one of them would be description of data. So this description of data could involve making plots or making histograms. And this is mainly for visualization purposes. It does not require any deep analysis on your part. And this is taught in school. So usually you're taught how to present, let's say frequency data using histograms, or to plot simple plots that have x and y coordinates, where x could be one parameter and y could be another parameter. And more than description of data, all of you also have used statistics in school, let's say for parameter estimation. Okay, let me actually not call it parameter estimation, but it would be called curve fitting. So you would have learned that if you have data given to you with x and y coordinates, then you can find a best fitting line that goes through all of these points. Obviously, it will not actually go through all of these points because the points are often noisy. So what usually would happen is that the points would be some scatter plot like this. then you have learned that there is a way to actually compute a line that actually goes through all of these points in some manner. And these are x and y. So, so this like you would have learned, and maybe like you have already encountered this thing called chi-square fitting, which is basically what one uses to actually produce such curves. Then we have statistics that can be used for things like uh, model testing, model or hypothesis testing. And you have been probably hearing a lot about this. So in this pandemic, once these vaccines were developed, we know that we are interested to know whether a vaccine is actually uh, efficacious at all, whether it cures you, whether it actually gives you any immunity, and whether one vaccine is better than any other vaccine that you might have. So all of these topics actually fall in this domain, model hypothesis testing. And there is a fourth use of statistics, especially in science and especially in physics, actually, which is to build physical models. So, for instance, all of you have heard about statistical physics, where we use some averaging techniques to derive a formulation that describes a large number of particles. Let's say particles in a room. These are atoms and molecules that are pumping around, colliding with each other. And to describe this sort of a situation, you may actually say that I need information about all the atoms and all the molecules, whatever they are doing. But for many purposes, that detailed information is actually not required. And all of you have heard about thermodynamics. Statistical physics actually derives for you thermodynamics. And thermodynamics is actually based on some average quantities that are familiar to all of you: temperature, pressure, and so on. So these are physical models that use statistics to actually even formulate them. But that's not the only place where you actually need them. In cosmology, for instance, we have a situation where we have many galaxies that are seen in the universe, and one is interested in asking how these galaxies came about. You can easily see that this question cannot be answered if we do not know the initial conditions in the universe absolutely in gory detail, where each particle was. So given any set of initial conditions, we know different kind of universe would emerge. So how can we actually test theories of formation of structures in the universe, how these galaxies form, without actually having a detailed information about the initial conditions? So the way to go about it is that we actually don't want to address it at that level, at the level of atoms and molecules. We want to address it at the level of statistics. So we ask questions such as, given a class of initial conditions that are described by some kind of statistics, what kind of universe would emerge, which can also be described only statistically? So for instance, you could actually be asking, what is the power spectrum of the mass distribution in the universe, and whether this power spectrum can be derived from the initial power spectrum. Now, both these notions, at the initial point and the final point of using the power spectrum, is basically a statistical tool that is described in statistics. And there are various other usage which one can find for statistics, such as in signal analysis. Uh, right now, when I'm speaking to you, the voice is going through the internet and it is being received. So there are various errors that can actually creep in, like, through the transfer of this data. But there are ways to actually minimize the loss of signal due to this noise. And sophisticated algorithms actually are used to do this. But even this Zoom application can do a little bit of signal processing to, let's say, like remove the echo that might happen, like, if I'm using the mic in the device, and the sound that the other people make, like, is also like being produced in the speaker. So there's a little bit of a feedback, that the feedback can actually be removed. So all of these are actually like broadly, like, these would be actually like statistical techniques applied to signal analysis. So there is actually a huge, so statistics is actually like, a huge topic which has many subtopics. And it is maybe like not known to you that statistics itself actually, it has two versions. So over and above, on top of this, I should actually put some arrows like this. So there are two kinds of statistics that one knows about. One is called, I'm sorry, something here. So one is called frequentist. Okay, I'm sorry, I don't know why this is happening.
I think on the edges there are problems, no? Edges maybe.
No, I actually have palm muting, but I don't know why it is not working. Okay. Okay, I think I have to, no. Okay, let me actually write it elsewhere. So basically, like, there are two kinds of statistics. One is frequentist, and the other is called Bayesian. So these are both ways in which one can think about statistics, and they're complete on their own. So problems can actually be, statistical problems can be analyzed using either of these two methods. But it turns out, like, Bayesian is a little more powerful and more intuitive than the frequentist statistics. However, due to various historical reasons, Bayesian statistics was not in favor until late 60s and 70s. Main reason being that, as it will become clear, like, in the later lectures, that Bayesian statistics uses something called priors. And there was a time, like, when scientists wanted all of science to be so objective that no subjective element could actually enter into it. Which is why they went for frequentist and frequentist methods. But frequentist methods actually lead to solutions of statistical problems. I mean, solutions are fine, but it is very difficult to be intuitive about them. So you actually have to say what you want to say in such a convoluted manner that it becomes hard to actually develop an intuition for it, unless, like, you work with those tools, like, for years. So I'll actually give you some examples of both of these things, both of these two statistics. And I'll not necessarily, like, discuss all of these subtopics. I'll maybe, like, focus a lot more on, let's say, like curve fitting, which actually, along with curve fitting, has this thing called parameter estimation. So till now, like, all these are just some terms that I'm throwing at you. So let me now get to the point and start with something very simple. So even to, like, understand whatever I've discussed till now, I have to actually start with something exceedingly simple. So let us say, like, you actually have a spring balance. Let's make a spring balance like that. And you're measuring the weight of some object that has mass m. Okay, so typically what you would do is you would actually put this mass on the spring, release it, and it will go up and down a little bit, and then due to friction it will kind of settle down somewhere, and wherever it settles down there will be a reading, and this reading you can actually say is the measurement of this mass. I'll actually call it, I'll use mass and weight interchangeably, and they only differ through some factor of g. So if you measure this mass once, you can again try it by again pulling this mass up and releasing it, and again it will oscillate a little bit before it actually settles down somewhere, and very likely it will now give you a different result. So it's not like the same answer that you will get each time, and I'll tell you why that happens. So you will actually get a set of masses, actually not a set of masses but a set of readings if you do it repeatedly. Now why you would get different answers, different readings, is because the spring is in contact with this device, which actually is this, where you actually have the reading. It's like little disc there. This little disc can suffer friction due to its contact with the encasing, in which it is put. And due to friction, this is like basically a simple harmonic oscillator with friction. But the friction is of the usual n mu kind. Okay. The usual, what is it called? The static friction and kinetic friction. There is another friction that you guys have probably encountered in physics, which is proportional to the velocity, some gamma v. Okay. And that gamma v has a different solution, and this sort of friction with simple harmonic motion has a different solution. So with that sort of a friction, it actually is possible that due to friction, when the motion damps down, the reading actually can stop abruptly, in some small range. And because of that, the reading is not actually going to be the same every time, because the initial conditions are different. But that's just the physics of the spring balance. There is also physics of air. So this mass is actually going up and down through air. And as it is going up and down through the air, air also has a little bit of resistance for anything that moves through it. And this is also not going to be the same. It is also possible that there is some wind blowing, or any number of, or maybe there is earthquake at or very tiny tremor of an earthquake at that very moment, which will actually shake this whole thing up. So all these different sources of noise will make the reading come out differently each and every time that you actually do this experiment. So then the question is what is the way to actually measure the mass of an object in as accurate a manner as possible. So you could, of course, just measure it once and give it as your measurement. And that measurement then would be something like this. So we'll assume that the mass actually has an intrinsic value, which is m naught. So m naught is actually its true value. We don't know what that is. We actually want to determine this m naught. All that I have is the spring balance on which I can actually measure the mass of this object, but that number, as we have already noted, is going to come out differently at different times. So in school, you have learned the following, that the mass will be written as, actually, first of all, let me actually write it like this. So this is mass, this is the reading. So let me define this as reading. So when you read the mass over there, that is your m. This is the intrinsic mass of the object, and some noise that actually creeps into this process, and you can't control it. So any specific instance of measurement could be like, one of those M1, M2, M3, and so on. So let's say like, you have measured it only once. So you have measured the mass as M1. So this is your reading. Okay, so you were taught in school that you have to write this in the following manner. So the mass M0, which is the unknown of the object, is then the reading M1 plus minus something that was called the least count. Let me actually say is delta M. So delta M was defined as the least count of the instrument. And what was that? Now again, like, you can actually recall that if you magnify a little bit of this, then you would have some readings like that. So there is a smallest reading that is there, right? So the smallest reading could be, let's say, in tens of grams, because although like, it's length, but we are now through the Hooke's law, we now are converting that into some force. So force like then measures the mass for me. So a little length here translates to some delta M. Okay. So you would have markings here, like maybe 5 kilogram, 5.1 kilogram, and so on and so forth. So the smallest marking that you have is like what you were told should be put there. Now, this is a very, very rough estimate of mass for the following reasons. One is that, as I've told you, the measurement process itself is such that if I release this mass, then the place where the reading would settle down, that depends a lot on the way, like, the friction interacts with this spring and this little disc over there. So there is that little bit of physics also going in. So how is it that the error bar that I have quoted, which is this delta M, is just related to the markings, the smallest markings on the spring balance? So clearly, like, that is the best that you can do in terms of visually. You can't measure mass better than that because there are no further markings. Okay, so you can only like do as good as that, but it is possible that the spring is actually doing worse than that. Why? Because, like, it is possible that when you take this measurement several times, let me actually make that diagram here. With the least count. Okay, so that's actually a little bit of a problem, like, when we do school physics, like, where we just use the least count, then obviously, like, you can see like there's a little bit of a problem there. Then how do I determine this delta M? Or, like, how can I, or I can ask another question, how can I improve upon this method? Like, here I'm just taking one measurement and then saying, like, that my mass is actually that measurement plus minus some error bar. But I know that the very next moment I could actually do another measurement, and that measurement will be some M2, and that will be M2 plus minus delta M. So clearly, like, there is no unique answer to this. I mean, the answer doesn't have to be unique, but there is a question that we can ask, like, can we do better than measuring it only once? And in fact, like, all of you have learned how to do that also. So what you were told is the following, that to measure the intrinsic mass, which is this delta M0, which is the quantity that we are after, what you can do is you can measure the mass many times. So M1, M2, M3, let us say we measure it some n number of times. Then you were told that the estimate of mass, estimate as in what should I quote for the value of mass of this object, is given by the average of all these masses, which is defined like this. I going from 1 to n. And there is a plus minus, which also you are told is actually given by the sigma, which I'll define in a moment, where sigma is called the standard deviation. So what do I mean by the standard deviation? What I mean is this. So take these measurements, the ones like that we actually have obtained by diligently measuring the mass several times. So several times we have measured it. Let me actually try to plot them on a line. So let's say this has mass m. This is your origin. So your M1, M2, all these guys are clustered in some manner. Okay, there may be more number of points somewhere, and then maybe fewer points outside. If I were to plot a histogram, it is possible that the histogram is possibly going to look something like, okay, maybe this is too big. Something like this. This is the distribution of points. So there are n measurements, and those n measurements, when I bin them in some delta m bins, then the number of measurements that fall in this range, in this little range, that's the height of this. So there are, in this little range, for example, there are many measurements, but outside here, there are fewer measurements. And you may also notice that I've actually made this histogram kind of go randomly up and down. So it's not going to necessarily be a very smooth, monotonic rise. So it's not that it has to rise monotonically and then go down. Because in statistics, because of probability fluctuations and so on, these numbers actually are never going to be the same. Each time you do this, it'll be a little bit different. So this is the sort of distribution that I get. And then the average value that we have computed here is basically the average of this data, which could be, let's say, somewhere there. So this is my average value, which we have a special name for. This is called mu. It's also called the mean. Mean, or we can call it the average. And that's just that. So that. And then we also know how to compute the standard deviation of this data. Okay. So how is that obtained is like this. So sigma square would be 1 over n, each of those measurements, minus the mean squared. Okay, so this is how one does that. And for the standard deviation, we'll, at the end of this whole calculation, we'll actually take the square root. So taking the square root, we'll get some number, and that number we are saying is to be put in this quotation of what the mass of that object is. So mass of the object is basically this average mu plus minus sigma. So actually I can write it like this. So m naught is m, mu plus minus sigma. That's what we are taught to quote. And I hope all of you are actually familiar with this. Now, in this course, basically, we want to figure out where all this is coming from. Why exactly we have to put a sigma there, and why mu appears there. Because again, if you go back to your school days, you would recall that when you were taught some basic statistics, you were taught along with the idea of average or mean, two other notions which were all called I think the term is something of central tendency. I myself have forgotten, but something central tendency. Measures of central tendency. All that it means is that when data is clustered like this, where there is some place where it is peaked, and then there are tails in which it falls. So there is a center where most of the data lies, and how to measure the place where that center is. There are three things like that you were taught. One was average, mean. The other was mode. So mode, if you recall, okay, I have now actually kind of destroyed this histogram. So mean is just this quantity, right? So mean is like nothing more than this. So it has to be computed from the data itself without any visual inspection. But the mode itself was something something like this. Okay, maybe like the data has even a bigger height there. Okay, data itself could be distributed in any which way. Okay, like I don't need to presume where it is. So the mode is basically this value here, which has the highest number of values falling in that range. So this is the mode. Mean is that quantity over there, and roughly mean is such that mean would for this data mean could be like somewhere over here. So mean is typically when there are roughly the okay, actually I can't use. So basically roughly when this area, all this area is roughly the same as the area on the left. Okay, which I can make it again. So mu is such that the areas are actually roughly the same. Okay. There is a third idea which we have also learned, and that is mode. Actually, sorry. This is actually not the mean. Sorry, this is not the mean. If the areas are the same, that is actually called something else. It's called the median. That is the median. So median is basically that point such that to the left of it there are a certain number of points, and to the right of it there are a certain number of points. If the points on the left are the same as points on the right, that is called the mode. And sorry, mean doesn't actually have this nice geometric intuitive meaning. It's just whatever it is. Okay. So then the question arises I have actually said that the quantity to be quoted is mean. But why mean? Why can't I quote mode, or why can't I quote the median? Now there are situations when actually it turns out that mean actually is the worst quote for the actual mass. A better quote would be median or mode, depending on something that actually cannot be analyzed just from the data. So data itself, like, it doesn't tell you, like, what to quote. It comes from somewhere else. It comes from probability theory. And I'll just give you one example of it. So let us say that there is a number which exists only between A and B, and we don't know what A and B are, but we can actually describe them by the center of this interval, and let's say the width of this interval. So there is a width in the center. So let us say, like, the width is actually known to you. Let me actually just say width is 1. Then the center is unknown to you. And this is like some value x, c. Now, I'm going to give you this fact. It's not going to be obvious to you, like, why what I'm going to say is necessarily true. That if some number is distributed in this range with equal probability, let me draw it like this, which means that there is equal probability for the particle, for this number to actually be in this range, and equal probability to be in this range or any other range, and outside the probability is 0. Then it turns out that if you actually have a set of numbers drawn from this sort of a distribution, so I only have xi's, various xi's. I don't know what xc is, but I know what the width is. Okay, so I have like a large number of xi's. I just know that xi's are drawn from this sort of a distribution where the probability of getting this number somewhere in some range is actually roughly, not roughly, I mean, it's actually equal. It's a uniform distribution. In fact, let me write that down. It's called a uniform distribution. Then it turns out that if you want to determine xc, the best that you can do is take the maximum value of the set xi. To that, you add the minimum value of xi and then divide that by 2. Okay, that is the best measure of this distribution. So what is being said is that the number of points, like, would be like there will be a large number of points like this. They will not go necessarily all the way up to B or like up to A. They can stop somewhere before that also. Take the maximum of that value, maximum of that set, and the minimum of that set. Those are like these values that you need to actually determine your xc. If you use this method, then you may be surprised that usually if you increase the number of points, then I'll show to you, like, maybe in the next lecture, maybe like a little bit later today, that your estimates actually become better and better. So we actually will learn this. So actually, for very large number of data set, sigma is going to be smaller and smaller. So larger the data, like, sigma actually turns out to be smaller and smaller, and I think, like, maybe like in school you have already learned that there is something like sigma by square root of n sort of a behavior that errors show. So larger the number of points, the errors on some way of quoting the value of the parameter go down like this. So larger the number of points that we use to measure our average, error becomes smaller like this. So this actually turns out to be true for the mean. So mean actually behaves like this. So mean, when you compute mean, the error bars on mean actually go down like 1 over square root of n. But for this, they go down actually like some sigma by, I don't recall, it's n or n power 1.5. it's actually, yeah, I think it's like more like 1.5. So they can't go down really rapidly, which means that you need very few number of observations to actually determine the center very accurately. Now, how do I know all this, and how do I use all of this to determine whatever, like, parameters or theoretical physical parameters, or, like, parameters of my theory, or like just my measurement? How to, like, use all these ideas in a manner, like, that it becomes intuitive, like, that I should be doing this or that. Because till now, like, I've just given you some prescriptions, like, which you have encountered in school. So, like, that you were told that you should do something. But where is it coming from, and how do I do better than this? So that is basically what this course is about. Uh, so let us then proceed with some formulations. Okay. So we'll again keep things simple. So what we have discussed till now is that when we are trying to measure the mass of an object, there is an intrinsic mass that we don't know, which we are interested in finding out. And there are errors that happen because of various reasons. And the whole thing looks like this. So formal problem is that there is something like m naught, which we'll call reality, which is the mass of the object. This gives rise to an observation, maybe like ith observation, and to the reality, the real mass of the object. Each time I make a measurement, some error is added to this ei. So I have access to this. I am interested in this. Okay, but I don't have a direct access to that. And maybe I know something about this. Now, this is the important point. Like, if I know something about this, then I can do, or rather, like, I can actually try to argue objectively how I can do better or worse, depending on like what I'm doing. Okay. So the end of the day, like, what I actually want from my statistical methods is the following: that I need a quotation for m naught given the data mi. So this is my data. Okay. So what I want is this. By the way, this actually may look like more. So let me make that not a little closer to this. So m naught. So m naught will define. Let me actually put a caret on this. And let me call this an estimator. So there is some estimator. Estimator is basically defined as some mathematical observation, mathematical operation carried out on data. Okay, so take data, do something mathematical with it, and the resultant is an estimate of the mass. So then you would say that the mass of the object is actually the estimator. Maybe I shouldn't actually have that. Let me actually just write it like this. So mass of the object, intrinsic mass of the object, is estimated to be the estimator, and plus minus some errors like that we also have to figure out, like how to actually determine what to put next to that. So for this, as I've told you, like all this actually becomes possible if I know a little bit about this distribution of errors. So what is the minimum that we can know about this distribution of errors? The minimum that we can know about it is that we can know its average, right? So maybe like I know, like, that it has an average which is 0. What that means is that sometimes when I make my measurement, I get a slightly larger value than the intrinsic value. Sometimes I get slightly smaller value than the intrinsic value. If the noise is unbiased, in the sense like it doesn't have a sense of only be like, higher than the measurement, then we can assume that it's going to go up above the actual value of the mass equal number of times as it will go below. I mean, only in an average sense. Obviously, like, in any given measurement, like, there could be like far more larger values than smaller values, but on the average. So what do I mean by that is that the distribution of EI, or rather, like, just let me like say E. So distribution of E is such that its average. Average is basically often denoted like this. So average is 0. Okay. But that is like, just one parameter that I may know about it. I may also know what is E square, sigma square. Maybe I know this also. So if I know these two quantities, then whatever I have told you about, that we can use the arithmetic mean and we can quote our results like this, that actually can be derived very easily, and I'll do it like, quickly tomorrow. But if I don't know just these two quantities, but I know a little bit more. So what do I know? I actually know the full distribution of E. So let me say that I know the distribution function of E. What that means is that I know P of E. Let me actually make a diagram for you, which will make all this abstract stuff a little more concrete. So let us say that P is distributed like some Gaussian distribution, like this. This is your 0, and there is some sigma like this. Okay. Let us say I know this. So I know that the error, the amount of error that creeps into my measurement each time I make the measurement is basically a random number that follows this distribution. And this distribution obviously, like, has 0 mean, which is what I was saying, that it's not going to always be giving you a larger value of your mass. Sometimes it will give you larger, but in equal number of times it will give you a smaller value also. So when you take the arithmetic mean of it, basically all those errors actually cancel out and you get the actual true value. Now, how does that happen? Well, this is very easy to see. Let me actually go back to my assertion, this. So let's go back to this assertion. Forget about the sigma bit, plus minus. So let me say, like, I want to ask. So when I said, like, I can actually quote the average. Now let me write like mu. So let us write down mu. Mu is 1 over n times the measurements, like that. Now formally, I know this is equal to 1 over n summation m naught plus ei, right? This is what it is. This is equal to 1 over n sum of m naught plus 1 over n ei. Now sigma m naught is just going to give me n times m naught, and then when divided by n, it will just give me m naught. Plus I have error averaged. Okay. So in each of those measurements, like it's going up and down in some manner, but like when I take its average like this, that's actually I'll show you like later on that actually this is equivalent to doing the following. You are doing this integral dE. Okay. Mathematically, it is that. Tomorrow we'll actually learn this. Today we don't have a lot of time for that. So when I take the arithmetic mean, it's of this. I'm actually computing its expectation value or the average, which since we have assumed it is 0, it will vanish, and you can see that mu, its expectation value. Okay, like what a not expectation value, but if I have a sufficiently large number of data points, then I know like the second term actually drops down very rapidly. Okay, we can see like that it's going to give me an average which is very close to 0. So this we can see like it's going to become better and better measurement of m naught. Okay, because this error like term like actually goes away. So all of this like we actually have to formulate in some manner from this probability distribution function. All right. So I have just 4 minutes. So let me see where I want to go with this now. Okay, what I'll do is actually I'll ask you to read up a little bit from those notes. Okay. Now this is like stuff like which you have already done in school, most likely. I mean, I remember like I did it in school, so you have also done it in school. So read some of this material, not everything. There is like joint probability and all like which is maybe going to be discussed later. But let's say this continuous random process, there are certain terms that are defined here. Okay, there's some expectation value which is defined in some manner. There's variance that is defined in some manner, and I have measuring simple physical quantity. So instead of mass, I'm measuring some, I don't know what it is. Time measured on a clock. Okay. So much of this like is like something which I've already discussed with you, but this is what I want you to do. Yeah. So go to 16. Now here, depending on those definitions that are there in these in this section, starting from 11 to 14, you are told that some expectation value of the mean is equal to T naught. And then there is another thing like, which is T bar square. T bar is just again, like these are defined in these notes. And there's some expectation value that is defined. And then it comes out as something. And then you are told that using this, it is easy to see that the standard deviation is this and something. Okay. So now this something like, we'll actually discuss tomorrow. But please go through this little calculation over here. And don't worry, like, you may not understand everything. And tomorrow we can actually discuss it a little bit more. And if you, by the way, like, at any time tomorrow, even today, you could have done that. If you have any question, you can actually ask me. I'm not able to see you or like whether you are even asking a question because I'm on the screen. So you can just ask and I'll respond. Okay. So we'll take it from here tomorrow. So this is your assignment till tomorrow. So I'll stop here and take any questions.
Thanks so much, Tarun. Thanks. I'll just check the chat.
Yeah.
Tarun.
But are the questions only allowed through chat or?
No, they can unmute themselves and they can ask.
So let them ask.
Everybody has permission. You can all unmute yourselves and ask questions. Yeah, if there are any questions, you can unmute yourselves. No, so Najam had the question, when you're referring to school, which school is that? Grad school or, no, or which school?
No, I think like it's taught in 9th standard, 10th standard.
Okay, okay.
I mean, I remember like learning it in school. Histograms.
Yeah, that's right. We all did it in school. It was the scoring part in the maths exam, right? Yeah, it was.
Hey, come on, like nobody has any questions. Don't feel shy.
Come on, please.
Okay. Maybe like they don't actually.
Yeah, let's see. Hope by tomorrow they should have some. Please.
Yeah, you can actually ask me questions about today's lecture tomorrow also. In any case,
there's one question. Sorry, there's where do we get the notes? It's on the website. On the website, click on resources. I've put it up over there. Okay. Yeah, sorry, Tarun, you were saying something.
Yeah, I'm saying like tomorrow actually it'll maybe like make more sense after they have looked through like my notes somewhat. Yeah, because I may have like used certain notions like which actually have not defined yet, like expectation value and so on and so forth. So anyway, tomorrow like it will be a little more organized and hopefully like they will actually follow it better.
And then by the time I shared it in the morning, then the session started, right? We started by 9:30 in the morning. So people didn't get time to see it. Okay. Fine. So thanks so much. Thanks a lot, Tarun. And see you tomorrow. See you tomorrow at 2. Yeah.
See you tomorrow, yes.
Yeah. Bye-bye.
Yeah, bye.
Thanks a lot. Thanks. Yeah. And okay. So Mark, I can see you are online. Hello.
Hello, Priya. Hi.
How are you?
Okay, thank you.
Yeah.
Is my audio okay?
Yeah, your audio is good. Your audio is good. I'll just make you. Yeah. Yeah. So Mark, your co-host, and
share my screen.
Yes, you can do everything. Yeah. So welcome, Mark Taylor. Mark Taylor, the students who have already attended Astronomy from Archival Data have already had a session with him, and we are really happy to have Mark with us from University of Bristol. He's the man behind TOPCAT. I think I'm one of the most faithful followers of TOPCAT. I mean, and I have these bunch of students who are also now using TOPCAT. And so Mark Taylor is the man behind it. And I would just like to just state that I have specially requested Mark to continue from what he did in the last session, in the sense we are not repeating basics, basically because I would like students to, participants to go ahead with their TOPCAT skills. Right. So in case there are people who haven't attended those, I would request you to go through that video in case you have some problem in understanding today. But it has been on special request that Mark is, going to go on a higher level because that's what we'd want to do. Right. So welcome, Mark, and thank you so much for being with us. And you can take over.
Right. Okay. Thank you, Priya. So yeah, I'll be talking about particularly cross-matching with TOPCAT. And yes, what Priya said. So this if you happen not to have come across it, TOPCAT's a desktop application for working with source catalogs, basically tables. And so, like Priya said, this isn't an introduction to it, and I'll be picking up where I left off last time. So if you haven't, I won't be going through the basics of how to start it up and how to load tables and so on. This is on a specific topic. And there's a link there to the previous talk that I gave if you want to look it up later. So what I'm going to be talking about today is particularly cross-matching. And so I'll explain what I mean by that. And then most of what I'll be doing will be a couple of demonstrations with some real data. So first of all, I'll look at matching some data in the region of the Pleiades using data from the Gaia source catalogue and from TOMAS, which is a large infrared survey. And we'll look at some of the options of how you can do cross-matching in TOPCAT with there for small tables and for large tables. And then the second demonstration will be looking at a different cluster, NGC 346, and I'll be comparing Gaia with Hubble Space Telescope data. And that will be more going into a bit more depth about how, once you've done the matching, you can work out what might be wrong with it and iteratively refine the work that you're doing to come up with better and better matches, because sometimes that sort of thing's required. I'll pause at the end of each of those parts to see if there are any questions, but since there's not an overwhelming number of people here, if you've got questions in the meantime, I can't see the chat, but if Priya wants to let me know, or if you just want to talk, then you can pass them on and I can answer.
So Mark, could you speak on a minute on, what are the advantages of cross-matching across catalogs? What is the motivation?
Sure, that's my next slide. So what I mean by cross-matching is when you have two catalogs and you want to work out which object in one catalog corresponds to which object in another catalog. So typically that might be if you're looking at multi-wavelength data and you've got a catalog which has perhaps from optical observations, and then you've got another catalog which is in the same part of the sky and you're doing infrared observations, and you've got a blob in one image which turns into a row in one table, and that turns into and you've got another set of blobs in another table, and you want to work out which rows in one table are really looking at the same object as which rows in another table. And if you just got a small number of objects, it's not hard, but if you've got lots of them, then that's a kind of mathematically complex process because they don't sit in exactly the same position. And so the way that you typically match them up is by saying, well, this object is near to this other object on the sky. So you can specify if there are two objects within, say, an arc second of each other in different catalogs, then those probably are the same object, but just different observations of the same object. And why do you want to do that? Well, often for doing kind of multi-wavelength astronomy of one sort or another. So for instance, if you can combine the infrared and optical and ultraviolet observations of the same thing and correlate those observations together, you can work out colors between those different observations of the same object in different wavelength regions, and work out an SED, and just generally find out more information about that object by combining different observations about the same thing. So TOPCAT gives you various different ways of doing that. And we'll go through them in the examples. And you can either do it between two different tables, and that's most often what you want to do, but you might also want to find whether there are objects which are close to each other in the same table, either because they're in a cluster maybe, or because you've got one table which amalgamates multiple different observations, and you want to see if you've got duplicate records in one table, or you might have 5 or 6 different tables which all correspond to different wavelengths or whatever, or different epochs, maybe observations taken at different times, and you want to match all those together. So there's options for doing that. There are various ways of telling TOPCAT which objects you want to be identified as the same thing. Most often that comes down to looking at positions on the sky. just saying that one thing is the same as another thing if it's within a certain region, but there are other options as well. And once you've done the match, again, there are different things you can do. So typically you'll create a new table which combines the values from the two input tables or the multiple input tables, but maybe you want to do something else like flag up objects in one table which don't appear in another table and so on. So TOPCAT gives you quite a lot of tools, but it doesn't do absolutely everything with cross-matching. It's not the last word on it. And so, for instance, something like it doesn't tell you what are the probabilities that an object is a match for another object. It just says it is or it isn't. It doesn't modify the criteria for whether something is a match or not based on whether there are lots of other potential matches nearby, which is something you might want to do if you're in a crowded region. So you might want to do more sophisticated things, and TOPCAT doesn't do all those. So if you want to really get serious about matching objects, you may need to move to different tools, but TOPCAT's often a good first step. And it also allows you to do lots of different post-processing and mucking about with the data once you've done it. So having got a match, you can then examine it closely, see what it looks like in correspondence with the original data, make selections, work out whether the match has gone right or gone wrong, and iteratively change the way that the results look. And it's good for doing that sort of thing. So there are really two different themes that you might want to use, two different sets of tools that TOPCAT gives you for doing cross-matching. The most straightforward one is if you've loaded tables into TOPCAT, you've got them sitting on your desktop basically, and if they're both sat in TOPCAT, then the easiest way to do it is to do all the calculations internally. So you use this match window, we'll see it in more detail later on, and you tell TOPCAT what your loaded tables are, and it does the calculations and then tells you the results. And that's straightforward. It's usually quite fast, and it works pretty well up to around about 1 million rows for each table. It can be more than that if you've got a bigger computer or you're prepared to wait a bit longer, but it's usually quite fast. But sometimes you need to work with tables that are much larger than that. So for instance, if you've got a small table locally, that some observations that you've done or that you've acquired from some paper that you've been reading, and you want to work out which of those objects is in the SDSS catalog, for instance. You can't download the whole of SDSS because it's too large. It's many hundreds of millions of rows. So it'd take too long to download, and it's too large really to work within TOPCAT. So in that case, you need a different approach. And that comes down to getting TOPCAT to take your table, send it to some external service. The external service does the matching with its local copy, with its copy where the remote service is of the data, and then sends the combined data back to you. And there's a few options for doing that. There's the CDS cross-match window using TAP queries. We'll look at both of these. And another option is multiple cone searches, which is not very efficient, but it's another way of doing the same thing. I won't cover that today. Okay, so I'll move on to the examples. I've got here the queries that I made for the two sets of data, so that if you want to do the same thing, you can you make the same queries and get the data yourself. I'll give the link to Priya or something later to put in the chat. So are there any questions up till now, or shall I plow on with the examples? I'll plow on. Right, so the first thing I'm going to do is start TOPCAT with 4 tables that I've already acquired from elsewhere. And the first thing I'm going to look at is data in the region of the Pleiades. And I have one set of data from the Gaia source catalogue. And this is more or less the result of one of the steps I did in my earlier tutorial. So I looked in the Gaia source catalog, I did a cone search in the region of the Pleiades, and then did a cut on proper motion. So all these objects are probably members of the Pleiades cluster. And then I've got another data set here, Pleiades 2 mass, and I'm going to overplot those on the same part of the sky, on the same plot. And this is all the objects in the 2MASS survey, which are in the same part of the sky. 2MASS is a large infrared survey, which is done in around about the year 2000, I think. I'm not sure about that date. So you can see there are lots and lots of 2MASS objects, these blue objects, and the red objects are the Gaia objects. And what I want to know is for each of these Gaia objects, is there a 2MASS object close enough to it that that it's actually the same thing? So this one, it looks like there probably is. These could be the same. But I want TOPCAT or something else to go through and work out what all those associations are. Okay, so the first thing I'm going to do is use this match, the pair match window. So I click on this button here. It's also in the joins window, which has some other options as well. For instance, matching for 3 tables or within a single table. We can use this one, the pair match. And all I have to do here, there's various options which I'll come to later, but basically what I need to do is fill in the 2 tables that I want to match with each other. So we have this one, Pleiades Gaia, and this one, Pleiades 2MASS. Up here it says how I define what counts as a match between the 2 tables. So I'm using the Sky algorithm. I'll explain the other options for that later. And for maximum error, let's say objects within 3 arc seconds. So what I want to do is for any of these objects, if I can find a Gaia object, one of these red ones, and a 2MASS object, and there's less than 3 arc seconds between them, then I want it to identify that as a match. This is just a first guess of what would be a reasonable number, and we'll refine that later. And then for each of these tables, I have to say which of the position columns, and it's worked it out for me. It knows that which of the RA and DEC columns, but if it doesn't guess those, then I can fill those in from the other columns in the table. And I push go. And so it goes off and does the calculations, doesn't take too long. And it says it's found 1,163 objects which are paired between the 2. And I get this button which says, do you want to plot the result? And I'll say yes. So if I plot the result, TOPCAT comes up with this window for me, which has got a graphical representation of what it's done. Let me make these spots a little bit bigger, just to make it more visible. And we'll have big blue ones for 2MASS. Okay, so you can see there's still the 2 objects, and it's done these. It's drawn these lines between the 2 objects where it's found an association. So this line is less than 3 arc seconds because that's what I asked it to do. And you can see some of them have found associations and some haven't. So that looks reasonable. When we look at the output table, so this is what it's generated as well as the plot, we can see, oh, let's have another look at the input table. So the input tables have got columns for the Gaia data. We have these ones, positions, some errors on positions, proper motions, and some photometry. That's the input Gaia table columns. The input 2MASS table columns are these ones. It's got 2MASS positions and again some positional errors and some photometry. And then if we look at the output table, this match table here, and we look at the columns, you can see it's got all the columns of the Gaia table first and all the columns of the 2MASS table second, plus 1 extra bonus column I'll come to later. And then if you look at the table itself, you can see all those columns on the left of the Gaia columns, on the right of the 2-mass columns, and each of these rows is one of the objects which has got an association here. So each one of these grey lines between the two objects corresponds to one of these rows. If I click on it, I can see which row it is. So it's highlighted the row that corresponds to that association. And so it's one object with observations in both catalogues. So why have I done that? Why is it useful? Well, one thing that I can now do is to do a color diagram, which uses both of the photometry in the Gaia catalogue and the photometry in the 2-mass catalogue, which I couldn't have done before because I didn't know which colors corresponded to which objects were which. Let me clear up some of these windows. So I can do a color plot here. In the Gaia catalog, there's this column BP minus RP, which is the blue minus red color in Gaia bands. And then there isn't a color column in the 2-mass catalog, but there are various magnitude columns. So I can do JMAG minus KMAG, and so that gives me a color in infrared. So I've got an infrared color versus optical color, color magnitude, color diagram here. And I can see these objects, they're mostly in the same cluster, and so they fall nicely on the same main sequence. Not all of them, there's certainly some outliers here, so there's something gone wrong, probably with the matching here, or possibly with the identification from the cluster. So let's see if we can identify a bit more what's going wrong here with these outliers. So what I'm going to do next is when we looked at the match table here, you could see the final column is this one called separation. And it tells you what it is. It's in arc seconds, distance between matched objects along great circle. So if I look at one of these, the separation column is the length of this grey line, how far apart these two objects are. And I can color the points in this plot by the value of that separation. So if I do a weighted plot and code it by separation, let me change the color map a bit. You can see that most of the objects are these green yellow ones, so they've got a separation of around about 0.7 to 1.1, say, arc seconds. But some of these outliers, they're blue ones, they've got much larger separation, up near 1.5 arc seconds. So it's likely that these ones with the large separations are probably incorrect matches. They're too far apart, they just happen to be close objects. They're not really corresponding objects between the Gaia and the 2-mass observations. That's also true of some of these ones with smaller values as well. So if the separation is less than, say, 0.5, then those ones look like they're not good matches either. Let's investigate that a bit further. If I do a histogram plot of those separations, so this is a histogram window, and I can choose in that table the separation column, you can see what the separations look like. So there are no matches with separations more than 3 arc seconds, and that's because I asked it when I did the match only to pick objects with separations less than 3 arc seconds. And most of them are around about here, around about between, say, 0.6 and 1.1 arc seconds. Most of those grey lines measuring the distances between the two catalogues. These ones here, the ones higher and also the ones lower, these are probably spurious matches. They're probably not real matches. They just happen to be objects which are close by. So what I'm going to do is go back to the match window and redo the match. But instead of using this maximum error of 3 arc seconds, I'm going to go and use a maximum error of, say, 1.1 arc seconds. And then that will cut out all of these large results here that we don't want to see. And so that's refining the match that we're doing by using the information that we've got looking at the previous match. So if I do that, I won't bother plotting that result again. But if I go to here and plot with the new catalogue it's made instead. Let me just do that. So that's the match we had with the 3 arc seconds. This is the match we had with the 1.1 arc second. And you can see at least those blue points down here, I'll flip between them again, have disappeared. So we've got a better match second time than we had the first time. That's because we've refined our matching radius. Okay, so that's kind of a basic match that you can do internally in TOPCAT. I'll just talk about a couple of other things in this window. So what we had initially was a sky algorithm, and what that means is just work out the separations between the objects using this maximum error value here. There are various different options for what you can do here. If you're matching not on the sky, you can match in 2 or 3 or more Cartesian coordinates if you've got objects that are in 3 dimensions somehow or other, various other things. I'll just go through one other option, which is this one, sky with errors. So this is similar. It asks us to input similar things, but I'll put in the same tables as before. But we have this additional column here. So as well as asking us for the positions, it's asked us for an error column. And what this is useful for is if you know in each table, you don't just know that there is a global positional error on the possible differences between the objects between the 2 catalogues, but you know for each object in the catalogue, in each catalogue, how big the error is on that. And that may be the case depending on where you've got that data from. And if you know that, you can put that value in here. And then for each object, it works out, well, is this one likely to be a match for this other one based on the errors, the positional uncertainties of those 2 objects. So in this case, we have got positional error information. If I go back to looking at the columns, we've got these columns, RA error and DEC error in the Gaia data. These are in milliarc seconds. So we haven't got a single error position that we can just paste into this error column, but I can write an expression down which corresponds to the positional error for the Gaia data. What I want to do is something like using Pythagoras to the Pythagorean distance. Let's see, RA error times RA error plus DEC error times DEC error. So that's in Pythagoras, the absolute size, the scalar size of the error based on these 2 input columns, RA error and DEC error. Actually, TOPCAT gives me a slightly simpler way to do that, and I'm going to use that function, which does exactly the same as I had before, but just with less typing, and it's this function of those two quantities. There's one other thing. This is in milliarc seconds, and the units here, it doesn't offer me milliarc seconds, it only offers me arc seconds. So I'm going to need to divide this value by 1000. So to turn it from milliarc seconds into arc seconds. So that's the errors in the Gaia data. If I look at the 2mass catalog, I can see, and again, there's something different here, error in, there's a major error axis and a minor error axis. So these aren't aligned with RA and DEC, but again, I can combine them to give me an absolute error. This time they're in degrees, so I'll do something similar. I can do high pot match min. And this time I need to choose degrees here.
Mark, I'm sorry.
Is that okay? Is there a question or shall I carry on? I'll carry on. Okay, so I now do the same thing, hit the go button, and it will go off and calculate the cross match based on those positional errors which are per object.
Mark, I'm sorry, you have divided by 1000, right? You cannot multiply.
It's given me no rows, which is disappointing, but is someone asking a question?
Yeah, it's me, Priya. In your error column, right, for Gaia, you have divided by 1000. Shouldn't you have multiplied by 1000?
You might be right. Let me see. So this is
It's
in
milliarc
the
seconds,
error
right?
values are in milliarc seconds. So they're for every 1000 milliarc seconds, there's 1 arc second. So I need value in arc seconds,
Okay.
and I had a value in milliarc seconds. Do you agree, or have I got it wrong?
No. It is in, you want it in arc seconds, right? But your errors are in milliarc seconds, isn't it?
Yeah. So if the error is 1 arc second, it's going to be 1,000 milliarc seconds.
Yeah.
Isn't that right? Have I done the wrong thing? It is possible I've done the wrong thing.
I think you have divided by 1,000. Should you be multiplying? You multiply milli by 1,000 to get arc seconds, right? Okay, or maybe.
Let's try it. Well, I get some results. Okay, well, let's see.
Okay.
Yeah, well, maybe you're right. Maybe you're right about that.
Yeah.
Okay, thank you, Priya.
Yeah.
Okay, well, so in that case, I do get the results. Okay, well, that's good. Okay, but that's how the per object errors work. Okay. Oh yeah, we'll try one other thing with that match window. So we'll go back to doing it with the normal sky matching, and maybe what I want to find out is not the objects which are the same between both catalogs, but the objects which are only in one catalog. So I want to find, if I can go back. What I want to see is the objects which are in the Gaia catalog, but which have no 2-mass counterpart for whatever reason. And to do that, I use the same general setup, but in this case, I choose one of the different options for join type. So 1 and 2 means I get as the output a table with both the with one row for each of the 2 input catalogs. If I choose 1, not 2, is that what I want? Yes, I want to find objects which are in the first catalog. They're in the Gaia catalog, but not in the 2-mass catalog. So I can click go there. And it's found the same number of matches, but this time it's found 41 rows in, it's created a new table here with 41 rows, and that's the objects which are in the Gaia catalog, but not in the 2-mass catalog. And I can again see what that looks like. So that's all of those, and I can overplot all of the 2-mass objects. So these ones, for some reason or other, these red ones don't have a 2-mass counterpart. And I don't know what the reason for that is. So I think in some cases it's because there's already a 2-mass counterpart which is closer to a different Gaia object. And for some reason, for some of them, it's not that. I won't go into the details for that because I don't know what they are, but you can investigate that. And that's another one of the kind of questions that you can ask. Okay. So now I'm going to go through a couple of alternative ways of doing that. So that worked okay. Both those tables weren't too big. We could get the results, but we can get the similar results using a different approach, which would also work if one of the external tables was very large. The most easy way to do that is to usually use this button here, the CDS cross-match window. Again, you can find it in the joins menu if you want to. It's here. So what this does is take my local table, and I'm going to be using the Gaia table, the smaller table here, and then sends it to an external service in Strasbourg, which has almost all the astronomical catalogs that you're ever likely to want to use. It's the Visier service, which has got 20,000 odd catalogs of published data. And it does the matching there and then sends back the results. I have to tell it which external catalog I'm interested in. In this case, I'll do the same one. I'll look at 2-mass. There's a number listed here. There's some of the most widely used and large catalogs in the menu, but there are, if you can find the Visier ID, which looks like this, there are many more that you can choose from. So I specify the external catalog that I want. It's got 500 million sources in it. And then the internal catalog. And again, I say which one I want and which are the positional columns. and I put in the match parameters, so the 1.1 arc seconds, which is what we decided last time, and then hit go. So then it takes my table, this table, sends it to Strasbourg. Strasbourg, they do the calculations very fast and then send the data back here. And you can see again, it's created a new table, this one with 1,157 rows. Is that the same as we got before? It's pretty close. So when I did it internally, I got 1154, and now I've got 1157. I'm not quite sure what the difference is, but it's almost the same result. And if I plot that, I'll see it does the same thing as before. One other way to do something similar is using TAP. So TAP, I went through it again in my previous seminar, and it's a much more complicated way of talking to external data services. I'm going to find a TAP service which has 2MASS data. Actually, there's quite a lot. I'm going to use this one, Gavo DC TAP. It's usually reliable. And so then this window is preparing to talk to that external data service, finding out what tables it's got, and telling me about them. So what I need to do is to write some sort of query here. Let me find the 2MASS table. It's here. That's all the 2MASS columns. I need to write a query here which will say, please take my local table in TOPCAT, send it to this external service. At the external service, please do the cross-matching and then send me the results back. It's quite a complicated query, but luckily this examples menu will help me to write it. So if I highlight the table that I'm interested in locally and the table in the TAP window that I want to cross-match with remotely, I go to the examples button here. I can go basically to the upload examples and choose this one, upload join. And then that writes in here a template query, which I can change around a little bit, but which basically does the cross match of my local table with the remote table 2MASS. So it says select, I don't just want the top 1,000, I want all of them. Select all the data from this remote table, 2mass.data, and then join tap upload.t1. What that means is take the table in TOPCAT, which is number 1. It's got number 1 in the table list here. Send it to the remote service, and then this thing says where the position of the local table, sorry, the position of the remote table is close to the position of the local table within, in this case, 5 arc seconds. Let's change that as well. So onto it within 1.1 arc seconds. I run the query. It's not quite as fast as the cross-match service because it can do lots more complicated things. The cross-match service is very optimized for doing just cross-matches. The TAP services can do all sorts of manipulations of the data, but it doesn't take too long. So we get the results back again, and again, it's got exactly the same result as the CDS value, 1,157 rows, and hopefully they're the same matches. So that's 2 options for doing it. One thing that you can see if I switch between these two, the CDS cross-match gave us 33 columns, and the TAP cross-match gave us 50 columns. The CDS service works very well, but it doesn't have all the column data in it. And so if you do a cross match and you get back a table that it turns out doesn't have the columns that you need, you might have to do something else, like for instance, use a TAP query.
Excuse me. I did the same. I got a message called right size limit of 10 to the power 8 or 9 exceeded.
So I can hear you a bit. Could you just, hang on, let me put my volume up a bit. Can you say that again?
Yeah, so I did the same what you are doing, and it shows me 10 to the power right size limit of 10 to the power 8 exceeded.
Okay, my guess is you must have done a did you I think you must be trying to upload a larger table than the one that I'm not uploading, the local table in TOPCAT.
Yeah.
Sounds like it's
I did a 2-degree cone search from your TOPCAT itself, and then I was trying to cross match it. So
right, okay.
probably
yeah, there's a limit on how large is the table that you're allowed to send up to the remote service.
Okay.
So yeah, that's one of the hurdles that you can come across. So you'll need to cut that down and then and send a smaller table and do that.
Oh.
It's worth saying the CDS cross-match service doesn't have that limit. You can send any size of table up to that. So I mean, yeah, you've come across something important, which is when you're trying to do this stuff, there's, you know, lots of things that can get in the way, and it's usually a bit of an iterative process of trying something out and seeing if it works, and then maybe run into problems and you have to do something else. Hopefully you can work it out in the end, but it sounds like you've made a good start anyway. Well done.
Thank you for
that. Any other questions on this before I move on to the next set of examples?
I just, Mark, Priya, I wanted to ask, you said that the CDS query will not give you back all the columns, right?
It's very difficult to hear you. I think there's some sort of echo.
Yeah. No, I'm saying the CDS query, right? When you do the CDS-1, you said it does not return all the columns, right?
Right. So it returns most of the columns that it thinks are interesting, but it might not have, for instance, some of the magnitude errors or something. I don't know. You know, you get back the positions and the basic magnitudes, but because of the constraints on disk size, basically, and processing amount available in the service in Strasbourg, they don't put all the data into the cross-match service. For reasons of efficiency, and so you just get whatever they think are the most important columns back. And if
so the advantage with CDS is you don't have a size limit, but with TAP you can get all the columns.
That's right.
So there's a play around between both of them, right?
That's right. So the CDS one is easier to use, it's much faster, and there's no size limit. So if that works for you, it's usually a good way to start. But if that doesn't work for you for some reason, and also not all tables are in Visio, there might be some that aren't in CDS, especially ones which are only recently published, and then you might need to find the TAP service which has got the ones that you want.
I would like to add that the CDS service worked for me, but the TAP was not.
Okay. Yeah.
Right.
So that the size restriction is fine then. Okay.
Yeah.
Okay, thanks.
And yeah, the CDS service is generally just easier to use. So yeah, in order of you know how you do things, if you can do it internally in TOPCAT, that's usually easiest. And then the next easiest is the CDS service, and then the next easiest is TAP usually. Okay, any more questions on that part? Good. Right, so I'll now do a different set of data. Clear up some windows. And what I'm looking at now is a cluster called NGC346. And there are some observations from a paper by Guillermis et al. For using Hubble Space Telescope observations. And this is from a paper which I've got the reference written down somewhere. I'll put it in the chat later, maybe. And you can see there are three, I think it's ACS observations here on the sky, and here's the cluster. And there's about 100,000 rows in this data set. And so on the same part of the sky, I've done a Kona search to Gaia and downloaded all the Gaia sources in that part of the sky. So I can overplot those. And that's where those ones are. And you can see there are more HST sources than Gaia sources, but there are presumably associations here. So what we'd like to know is which of these HST objects have got Gaia objects associated with them. So let's go and do what we did before and do a cross match. I'll start off with 1 arcsecond because that's the default. So we do the Gaia and HST. Go back to a normal match, and this time for the match selection I'm going to choose all matches, so it's not just going to pick the closest object, it's going to find all the matches it can. If I push go, off it goes, plot the result. And zoom in and take a look. So this is something similar to what I had before. But if I look at the results, oh dear, they look horrible. These red Gaia objects have many associations with the blue HST objects. And the problem is that the match radius that I put in is much too large. So there are lots of objects within 1 arcsecond of each Gaia object. Lots of HST objects within 1 arcsecond of each Gaia object. And that's not because they're the same thing. They just happen to be close. So my match radius is wrong. Let's try and refine that like we did before. So I can do the same thing. Look at the separation histogram in the match table. And you can see these are the peak objects, but below and above there's quite a lot of spurious objects. So the first thing I want to do is restrict it so that these larger objects, larger separations don't appear. So I'll redo the match with say 0.4 arcseconds as a match maximum radius. Let's try that. So that's an improvement. That's definitely better. Most of these objects have just got one association, but there's still definitely some problematic ones. So there's 2 here, and it's not really obvious which one of these is correct. They're both quite, similar distance, but maybe one of them is the real object and the other one's spurious. And there's quite a few of those, especially in the more crowded regions. So we still need to tidy this up somehow. So I'm going to go into a bit more detail about where those offsets are and try to work out what's going wrong and try to sort it out. I'm going to look at this match table and oops, not that. Look at the columns in the table. And so here we have the Gaia columns up to here, and the 2 mass columns down to here, and then the separation. The first thing I'm going to do, just to avoid confusion, so the positions coming from Gaia are called RA and DEC, and the positions coming from the HST are _RA J2000 _D J2000. I'm just going to rename these columns so we don't get confused. And I just do that by double clicking on their names in the columns window and changing what's written there. So I'll call the Gaia ones RA Gaia and the HST ones RA HST and DEC HST. Okay, so that hasn't changed any of the data at all. It's just changed the names. And now what I'm going to do is look at the difference between these values. So if I look at one of these associations here, the separation column that we already have gives me the length of this line. What I want to know is the distance in RA between these two, the length sideways, and the difference in DEC between these two, the difference kind of vertically. So what I'm going to do is add a new column, delta RA, which is the difference between the RA of the Gaia and the HST, and do the same for declination, delta DEC. So now down here, I've got these 2 extra columns, delta RA and delta DEC, and if I look in the table, I'll see them there as well. Now what I can do is plot those 2 things against each other. So if I plot delta RA and delta DEC, you can see something interesting. So this is really just a 2-dimensional analogy of the 1-dimensional separation histogram that we had before. Most of these are spurious values. They just happen to be associations. So these are objects which are sat right on top of each other at 0, 0, but they're not the real associations. This cluster here are the ones that are real associations. So I can identify these by making a subset of them. I push that blobby button and do a little circle around them. And I'll call those true match. And if I then go back to the match window, use this subsets window. So if I can find one of these matches, so this is one of these objects with multiple apparent associations. If I turn off all and just leave the true matches, it shows me this one. So now this looks much more healthy. All these objects have only got one association, at least pretty much all of them. And you can see they're all offset in about the same way. So why is that? Why aren't these objects sat right on top of each other? Because normally you'd expect that they should be centered around 0. That would be your kind of obvious idea. Well, there's one possibility is that they might have some proper motions. So they have got proper motions. And the HST data was taken in, I think, about 2004. And the Gaia data has an epoch of 2016. So in that time, maybe the whole cluster has moved across the sky, which means that they've drifted. So if you could work out where the Gaia objects ought to have been in 2004, maybe we'll get a better result, or a result with with this offset closer to 0. So let's try that. We can do that. In the Gaia data, we have these columns, as well as the RA and DEC. We've got proper motions in RA and DEC, plus parallax and some other things. And in TOPCAT, there's a function which lets us work out, so if we look in the functions window, there's all these useful functions that let us do algebraic manipulations on the columns. If I go to Gaia, I can find this one, epoch prop. And what this is a function which, if I feed it a position and a proper motion and parallax, and if I've got it radial velocity, and time in years, forwards or backwards, that I want to work out where those objects would be in the future or would have been in the past, it can tell me those positions. So I'm going to use that. So I'll add another new column in here, which I'll call POS 2004, the position where these objects would have been in 2004. And I'll use that function. So this is the difference in years between the Gaia nominal epoch 2016 and the HST epoch, which was about 2004.6. And then I feed it the positional information that we have from Gaia. I'm going to put in 0 for the radial velocity because we don't know what it is for most of those. I made a mistake. That's because I didn't use the right name for the position columns. I renamed them. If I now look at the table, what it's given me is a new column which has got an array value, which has got all the information about the proper motions and positions that this HST object would have been, sorry, where the Gaia object would have been in 2004, rather than where it was observed in 2016. I'm only interested in the first 2 elements of those, which is the position in RA and DEC. So I'll make 2 new columns which extract those just to make it easier to use. So I can call those RA 2004, which is POS 2004, the first element. Same for declination. So I can now look at the positions of those things with an overplot. won't bother making a new column this time. I'll do RA 2004 minus RA HST. And this is the result. So if I look at this, you can see the distance in the associations has moved a little bit towards the center, but not much. And so the idea of the proper motions was a reasonable idea, but it's not nearly enough to account for the discrepancy between the positions of the Gaia objects and the positions of the HST objects. We're getting to the end of the time, so I won't go through in detail what that is, but it turns out the actual reason is the absolute astrometry difference. So the absolute astrometry of Gaia is pretty much correct, but the HST, although the relative astrometry is very good, it just didn't know exactly where it was pointing on the sky when it recorded those positions. And so there's an offset in those values. What you could do if you wanted to improve it further is to go back to the HST observations, work out what the difference is between here and the center, apply that to the HST positions, correct the astrometry in the original HST data, and then redo the cross match, and then you'd have a somewhat better result, which would be centered on 0. Okay, so that's all I'm going to say. We're close to the end, but I'm certainly happy to answer any questions if there are any. It was quite intense, so well done if you managed to keep up with it.
Yes, so you could unmute yourself, or you could put your question on the chat window, right? Anything is fine. Mark, I have another question, sorry. But for this cross-matching, at present, there isn't anything to use a third criteria, right? Like, for example, its magnitude or something like that for the to give it some weight in matching?
Yes, there is. So that's one of the options here. If I choose, let's see, Sky plus X.
Oh, wow. Oh, these are new additions. I didn't know these
That's
things.
been in there for a very long time. But one of the problems is there's so much in that it's difficult to find what you're looking for. But if you go to this help button, let's try it out.
Okay.
So it takes you to the help browser for the window that you're interested in. So that's this one, and you go down here. And so if I look in the match criteria box bit, go to that, follow that link, and then it tells me some description about what all the different types are. So sky with errors, blah blah blah, sky plus X. So you can work out, you as well as positions, you can put in a magnitude in one table and a magnitude in another table. Getting the inputs right for those is quite difficult because you might need to end up scaling the magnitudes so that the difference in one magnitude doesn't equal the difference in 1 degree because of distances. But yes, in principle you can do it.
Okay. But if, for example, you use the Gaia matches for the Gaia ADQL, right? Gaia itself does the matching business, right? And I think that is a more reliable match than is that more reliable?
So you're talking about using the TAP service. It's not more reliable. I mean, as long as you understand what's being done. I mean, the Gaia matching mostly will do exactly the same as the TOPCAT matching is doing, which is sorry. Are you talking about the pre-match tables within?
Yes. I'm talking about the pre-match table which Gaia provides.
Yes,
with
okay.
Matching with 2 mass and Ys and stuff.
Sure. Yeah. No, you're exactly right. Those have done much more careful matching, and those are doing more sensible things, more thought through things than TOPCAT's doing here. So yes, I didn't mention that at all, but that's a very good point. If there are pre-match tables available in the Gaia service, for instance, that's going to be much more reliable because it does things like take into account Bayesian probabilities about whether something's likely to be a match, and so on, depending on the density of sources in that area. So yeah, good point.
Okay. Yeah. Okay. Thanks. And the others can ask their questions. Actually, tomorrow I'd be doing kind of a follow-up of what you're doing is basically combining Gaia with spectroscopic data, Gala, Apogee, etc. So that can also be done well with TOPCAT, right? If you do it like that, or
well, you can join two catalogs. What exactly have you? How are you going to be doing that, or what is it that you're trying to do?
No, to match it with the spectroscopic data available, say from Apogee or from Gala or from some other. But then that would one would need to do it similarly like that, right?
Yeah, as long as positional matching is what you want, then these techniques will work for that. Yeah, if you have positions in the catalogs.
Okay. 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 Fine. And the others, I'm waiting for the others to ask some questions.
I don't have a question, but probably we could be getting those tables, or you used the tab services or the cone search, the offline tables.
Could you repeat your question, Avik?
Yeah. So the offline tables Mark used for the cross matching, where they were obtained from VO cone search, or they were proper offline tables. So if I can get the specifications or the tables in anywhere else.
Where those tables came from? Hang on, let me put into the chat the URL. Right, so if you go to that URL, you'll find those tables, they're FITS files. So, and at the PDF that's there has also got links. It's got a description of where I got those data from. So it's got ADQL queries for the two that I got from TAP services, and it's got cone search queries for the two that I got from cone search.
Yeah. Thank you for that. I already.
Yeah, you can just download those tables directly from there if you like.
Yeah, I've already done that. You send it and I went. Thank you.
Okay. Actually, Priya, maybe you could put that information into the online resources.
Yeah. I'll add it there. Thank you. Thank you. Yeah. So any more questions? So actually, just to mention, a lot of the students did various projects in the previous, astronomy from archival data. And a lot of them have used TOPCAT for their, analysis. So in that way, it does not come directly as a TOPCAT project, but it's a project which, implies TOPCAT.
Oh,
that kind
great.
of
Good.
Though then the step 2 was then told to them that then they should write their Python code for the same thing, try it out first with TOPCAT. And that's exactly what even I do. Try it out first with TOPCAT, and then, then you can write your code and check it out with that. Yeah. So that's what they did. Yeah. Okay. So I don't see any more questions. So thanks a lot, Mark.
Okay. Thank you.
We hope to still keep in touch, because the Astro Sprint thing is a series of 3 workshops, right? I think you're aware. So since it's Star Trek themed, this is Enterprise, then we have Discovery, and then we have Next Gen. So I do hope to have you for the next one too, so that we progress further with TOPCAT. Right?
Okay, we'll see about that. But good luck for the rest of the workshop anyway.
Yeah. Thanks a lot.
Okay.
Thank
All right.
you.
Bye-bye.
Bye-bye. Bye. And we meet in 15 minutes, right? In 12 minutes, rather. Yeah. For the participants, yeah. In 12 minutes, we finish our tea break, right? So 4:15, we have Professor Deshpande. And then you have Tim Hamilton after him, right? So please get a fast cup of tea, and then we meet in 12 minutes, right? Yeah. See you. Bye-bye.